Alright, so today we're going to be talking about the concept of finding the length of a curve. So just to start with the basics, the formula that we're going to be using to find the length of a curve between 2 points, point A and point B, is the integral from A to B of the square root of 1 plus dy dx squared dx. So let's move on to figuring out why that works. So if you take a look at this diagram right here, you could see that we've got it set up here that we've got the curve y equals f of x, and we're trying to find this arc length outlined here in yellow. So the first thing that we're going to do is we're going to imagine that this curved arc length is divided into line segments that are infinitely small, and they're going to have a length of s. And so now what we're going to do after that is try to imagine those line segments in terms of dy and dx. So we can see that the horizontal component and the vertical component of this right triangle with the hypotenuse of s would have the legs of dx and dy. So now we can see that if these line segments are infinitely small, the arc length is going to equal the integral from a to b of s. And now that we have this right triangle with dy and dx, we can say that the arc length is going to be, we can say that s is going to be equal to, using the Pythagorean theorem, the square root of dx squared plus dy squared. And therefore, we can say that the length of the curve is going to be the integral from a to b of s, or as we now know it, the square root of dx squared plus dy squared. We're close, but not completely at the point where we can prove the formula up here, so there's just a few more steps. The first thing we're going to do is we're going to take this dx squared and we're going to factor it out. So we factored it out, it's right here now, and if you put this back in, just, using FOIL, you will get the original that we had. So once we factored that out, just take the dx squared out of the radical, and we are going to get this right here, which is the integral from a to b of the square root of 1 plus dy dx squared dx, which is the exact formula that we have been using so far. So now let's move on to an example. The example says to find the length of the curve y equals ln of secant x between the x values of 0 and pi over 4. So our first step is going to be to use chain rule to find dy dx. So if you don't remember, chain rule says that the derivative of f of g of x is going to be f prime of g of x times g prime of x. And so we take chain rule and we apply it to this function that we have right here, and we get this, and we can simplify it to secant x tangent x over secant x, which just equals tangent x. So now we know that dy dx is equal to tangent x. Now finally, what we have to do is just use the formula that we just proved for the length of a curve, plug everything that we have into it, use some simple antiderivatives, and come to our answer. So we're going to use the formula that we had, the integral from a to b of the square root of 1 plus dy dx squared dx. And we're going to have dy dx squared is going to be tangent squared x, and a is going to be 0, and b is going to be pi over 4. So now we use our identities, and we know that 1 plus tangent squared x is equal to secant squared x. We simplify that to the absolute value of secant x. And then eventually we get to this antiderivative, and finally we get to this answer. If this was a bit fast for you, you can pause and look through the steps and see how exactly we got from each step, or you could also go on the internet and look at a derivative calculator if you want to see an even more in-depth breakdown of this. Sorry, an antiderivative or integral calculator, if you don't understand it. But yeah, essentially we just have our answer now that the length of the curve is ln of root 2 plus 1 units. It's a pretty simple topic and it's pretty useful in calculus. Alright, hope you enjoyed. Bye.